One of the advantages of Demoivre's theorem, what it's really useful for, is proving some of our trig identities. And we can prove them in a lot quicker and neater than we did in the past. So, for example, this one, now obviously we know what these relationships are, cos 2 theta and sin 2 theta, but we can actually prove these very quickly. Because what I now know is that cos theta plus I sin theta squared, I can rewrite as cos 2 theta plus I sin 2 theta by the theorem we saw yesterday. But if I expand the right-hand side out, I'll get cos squared theta plus 2I sin theta cos theta minus sine squared theta. And what we saw about complex equations is the real part must equal the real part, and the imaginary part must equal the imaginary part. So therefore, cos 2 theta is cos squared theta minus sine squared theta, and sine 2 theta is 2 sine theta cos theta. So it's kind of a neat little proof, very quick, but obviously we need to know complex numbers to be able to do it that way. So let's push it a step further. Let's have a look at sine 3 theta and cos 3 theta and tan 3 theta. And you may remember when we looked at these, once we got above 2 theta, it took a while to develop those relationships because we had to repeatedly apply the theorem. So let's have a look at this one then. So cos 3 theta plus I sin 3 theta would be cos theta plus I sin theta cubed. So I can expand the right-hand side out. Cos cubed 3I sin theta cos squared minus 3 sine squared cos, and then minus I sin cubed. Equate real and imaginary. And there's an expression for sine 3 theta. Now, if I want it all in terms of sine theta, okay, I'll sub in 1 minus sine squared for cos squared, and then that's all in terms of sine. And cos 3 theta, and similarly, if I want it all in terms of cos, then I can exchange 1 minus cos squared for sine squared, and we've got our results, which, again, a lot quicker. Tan 3 theta. Well, of course, we know tan is sine on cos. Now, the way to do this is not to substitute in the last step when it's in terms of all in terms of sine and all in terms of cos, but actually the first expression that we got. So on the top, I've written the 3 sine cos squared minus sine cubed, and on the bottom, the cos cubed minus 3 sine squared cos, because what I can now do is divide everything by cos cubed. And the reason I picked cos cubed, we're trying to turn it into tans. And we know tan is sine on cos, so it makes sense to divide by cos. And because we've got powers there, I'm going to divide by the highest power. So I'm going to divide everything by cos cubed, but then we see a whole heap of cancelling that'll happen. So the first term becomes 3 lots of sine on cos. Oh, what do you know? That's tan. The next one, sine cubed on cos cubed. Oh, that's tan cubed. And then on the bottom we get cos cubed on cos cubed. Oh, that's 1. And the last one there, sine squared on cos squared. Well, that's tan squared. So we can rewrite it now in terms totally of tan. But as I say, in order to do that quickly, use the first line when it's a mixture of sine and coses, not the last line when you've got it just in terms of sine and cos. It's a lot quicker to do it that way. We've seen some like this when we were looking at polynomials. You might remember in the extension questions. All right, we're going to show that x is cos pi on 9. That is a solution to this particular polynomial equation. So I'm going to regroup it. The regrouping, of course, I've done here is using what we just proved before. You might see that pattern, 4x cubed minus 3x. If I let x equal cos theta, then I can substitute in, because this now becomes 4 cos cubed theta minus 3 cos theta. But that's what we just said cos 3 theta is. And we end up with a very easy equation to solve. Cos 3 theta is a half. And we can do that. It's one of our exact values. So 3 theta will be pi on 3. The next solution will be 5 pi on 3. And the next solution, 7 pi on 3. Now, why did I stop there? Well, the reason I stopped there is it's a cubic. And I know we're going to have no more than 3 solutions to a cubic. Remember, we saw that in polynomials. The order is 3, maximum of 3 solutions. So I only need 3, and they're 3 consecutive solutions. That's 3 theta. So divide by theta, I get pi on 9, 5 pi on 9, and 7 pi on 9. But of course, the question wasn't find theta, it was find x. And we've said x is cos theta. So now I can say, oh, well, that means my solutions for x, cos pi on 9, the one they wanted me to show as a solution, cos 5 pi on 9, or sine 7 pi on 9. Sine? What happened there? How'd that become sine? That should be cos, of course. What's going on? There must be a little cut and paste error from somewhere. Okay. Okay, so therefore cos pi on 9 is indeed a solution. The other way, of course, that would have been perfectly valid for this, because it says show, I could substitute in cos pi on 9 into the equation and show, oh look, it does come up with 0. All right, now it's asked us to evaluate cos pi on 9, cos 2 pi on 9, cos 5 pi on 9. Well, it's playing with the roots of the equation. We now know the 3 solutions, which are the 3 roots. So we know these are the sine, it's there again, cos are the roots of 8x cubed minus 6x minus 1. The product of the roots for our equation will be 1 on 8. So therefore, phew, it's cos. Cos pi on 9, cos 5 pi on 9 times cos 7 pi on 9 is 1 on 8. Well, that's not quite what we want. We want 2 pi on 9 and 5 pi now. So now I have to play around with some of the trig relationships that we know. For instance, cos 7 pi on 9 is the same as minus cos 2 pi on 9. 7 pi on 9 in the second quadrant, so cos is negative. The acute angle would be 2 pi on 9. So cos 7 pi on 9 is the same as minus cos 2 pi on 9. So that's how I can get my 2 pi on 9 in there. So now, what have we got? Oh, well, 5 pi on 9, we've got all that we need now, haven't we? We've got a 5 pi on 9, a pi on 9, and a 2 pi on 9. So therefore, if I know those 3 things multiplied together are positive 1/8, because 7 pi on 9 is the same as negative cos 2 pi on 9, then this expression must be negative 1 on 8. Now, this particular relationship comes in very, very handy, the ones we are about to prove. Sometimes they'll ask you to find it. If they don't, it's perfectly okay to quote it. Okay? So we're going to find these 2 expressions. Well, z to the power of n, using Duhal's theorem, would be cos n theta plus I sine n theta. 1 on z to the power of n is the same as z to the power of negative n. So that's going to be cos negative n theta plus I sine negative n theta. I'm going to play around with this expression as well, using the idea of odd and even functions. As you think of your graph, cosine is odd or even? Yeah, it's an even function. If you were to look at the picture, it would reflect in the y-axis. So therefore I know function negative x is equal to function x. Sine, odd or even? Right, that one's got the rotational symmetry. So I know function negative x is equal to negative function x. So I can rewrite this as cos n theta minus I sine n theta. Now, we wouldn't just pull that out of the thin air in an exam. We'd probably write some sort of reasoning down. I can say, well, I know cos is an even function. That's probably more than I'd probably put in a test. I'd probably just say, well, cos is even, sine is odd. But there's our explanation why I can do that. So now if I add them together, well, the I sine thetas are going to cancel, and I get 2 cos n theta. So I say that particular relationship can come in handy for some of the questions we get asked. So z to the power of n plus 1 on z to the power of n. And the subtraction one, in this case, the cos n thetas will cancel, and I'll be left with 2I sine n theta. So something like this is where it comes in handy. If I want to now express cos cubed in terms of cos and multiples of theta, what I can say is this. 2 cos theta cubed will be z plus 1 on z cubed. Just using this relationship, 2 cos theta, well, n is now 1, will be z to the power of 1 plus 1 on z to the power of 1. I can expand out the right-hand side. So we get z cubed plus 3z plus 3 on z plus 1 on z cubed. And I group together the terms with the same coefficient, and look what happens. I get z cubed plus 1 on z cubed. They all have the coefficient of 1. And z plus 1 on z, they have the coefficient of 3. But now I'm going to use this relationship again. Z cubed plus 1 on z cubed, well, n is 3. That'll be 2 cos 3 theta. And z plus 1 on z, well, n is 1. So I can rewrite it 8 lots of cos cubed, because remember we cubed the 2 as well over here on the left-hand side, will be 2 cos 3 theta plus 6 cos theta. Divide both sides by 8, and we come up with a relationship for cos cubed in terms of n theta. Okay, that'll do us for today. So 7b, just a handful there I've picked out to play with.